Great. Now we can discuss about triple integrals in spherical coordinates. Let's say we want to evaluate the triple integral f of x comma y comma c dv over a solid domain E. Then in a spherical coordinate system, this triple integral becomes another triple integral. Now we want to express this integrand in terms of rho, theta and phi in terms of the spherical coordinates. We know that x equals to rho sine phi cosine theta, y coordinate equals to rho sine phi sine theta, and c coordinate equals to rho cosine phi. And then here's the interesting part. Then we want to express the volume element dv in the spherical coordinate system. In the spherical coordinate system, this volume element dv becomes, I don't have enough space here, so I'm going to write it here, rho squared sine phi d rho d theta d phi. So this is the order of integration that I usually use. First I integrate with respect to the rho variable, and then theta, finally with respect to the phi variable. And now these six limits corresponds to the solid domain E. Now as a special case I will write, let's say rho is a distance, so the inner integral goes from, let's say, a to b. Theta is the angle, let's say some angle alpha to beta, and phi is also an angle, let's say gamma to delta. So okay, let's say here E is a solid domain, given by, so E contains the points such that rho values are in between a and b, theta values are in between alpha and beta, and phi values are in between gamma and delta. Okay. I think this is the most interesting part, and in this class I am not going to prove this volume element result. But remember, in a spherical coordinate system, your volume element dv becomes rho squared sine phi d rho d theta d phi. And here is an image of the volume element dv. So this spherical wedge is the volume element in volume element in spherical coordinates. This looks complicated, but when we do examples you will see these integrals are very simple to integrate. Okay, so let's consider the first example. let's say we want to use spherical coordinates system to evaluate the volume of a sphere with radius 2. So basically this domain is a sphere with radius 2. This problem says find the volume of the sphere x squared plus y squared plus c squared less than or equals to 2 squared. It means this boundary is a sphere with radius 2. Good color. Okay, so this is a sphere. Maybe we have a similar circle like this. This x-axis, y-axis, and the c-axis. And equation of this sphere is x squared plus y squared plus c squared equals to 2 squared. That's the boundary of the domain. Okay, now so the volume equals to triple integral of 1 dv over the domain E, where your domain E is this sphere. Okay, so that's your domain E. Okay, now of course we are going to use spherical coordinate system to evaluate this triple integral. Okay, now volume element dv equals to rho squared sine phi d rho d theta d phi. Now we have a full sphere. Rho is the distance from origin to point in R3. Since we need to cover entire sphere, rho goes from 0 to 2 because the radius of this sphere is 2. Now angle theta is on the xy plane, so we need to cover this entire xy plane. Therefore theta goes from 0 to 2 pi, and angle phi, so this is our angle phi. The lower limit of angle phi is 0 and the upper limit of angle phi should be pi, and the reason is this. So if you want to cover not if actually we want to cover the southern hemisphere of this sphere, so then this is your angle phi. So the maximum value of phi should be pi. Great. Now let's integrate this. My first variable of integration is rho squared. Therefore we can treat this sine phi as a constant. Okay. So we have integral from 0 to pi, integral from 0 to 2 pi. Let's take sine phi term from the inner integral. Then we have this d rho d theta d phi. Okay, integral of rho square